This is SPARF, neural radiance fields from sparse and noisy poses. Our goal is novel view rendering given access to only few wide baseline images with noisy camera poses. This is shown here. Given these three images and their noisy cameras, we want to train a NeRF that will produce realistic looking renderings with an accurate geometry. This is exactly what our SPARF is doing. It is a joint pose-NeRF training strategy that exploits multi-view geometry principles. In particular, we adopt the NeRF framework and introduce two additional constraints. Here we compare SPARF with alternative joint pose-NeRF refinement approaches. As visualized in the depth maps, our approach is the only one learning a meaningful scene geometry. It is also the only one producing good-looking RGB renderings. On this forward-facing scene, our SPARF leads to sharper renderings with much less floaters than competitors. Our approach is applicable to any scenes. Again here, the scene reconstructed by SPARF has a much more accurate geometry. Let's look at SPARF in more details. NeRF produces high-quality novel view renderings under two conditions: dense input views and very accurate camera poses. This is the case in this example. However, when only few input images are available like here, NeRF heavily overfits the training views. It leads to very bad scene geometries and therefore low-quality novel view renderings. Some approaches have recently tried to improve the performance of NeRF in this few-view setup. This is the case of DietNeRF, InfoNeRF, RegNeRF, or DSNeRF, to cite a few. They achieve impressive performance in this setup. However, all these previous work assume perfect camera poses as input, which is an unrealistic scenario. Why is it an unrealistic scenario? Because how do we get the input poses? The standard is to use a structure for motion approach such as CoolMap. However, on few wide baseline images like in our scenario, the performance of CoolMap drastically degrades. As a result, in a realistic setup, it makes sense to assume that we only have access to noisy camera poses as input. Some previous works have tried to jointly refine noisy camera poses while training the NeRF. This is the case of BARF or SCNeRF, to cite a few. However, they assume dense input views. When only few input views are available instead, they fail. This is illustrated for BARF here, where we see that the renderings are not looking good. So in this paper, we want to solve the very challenging scenario of few input images as low as 2 or 3 with noisy camera poses. We propose sparse pose adjusting radiance fields, or SPARF, a joint pose-NeRF training strategy. We are the only ones producing realistic looking renderings with an accurate scene geometry in this challenging setup. So how does SPARF work? We adopt the NeRF framework and include two additional constraints into the NeRF optimization. Importantly, to design this constraint, we exploit multi-view geometry principles. Now let's go through these two constraints one by one. Firstly, we use a pre-trained correspondence network to extract matches between every pair of input views. We then use these matches in our first constraint, the multi-view correspondence loss. Let's take the example of this image pair and this particular match. Our multi-view correspondence loss minimizes the reprojection error between the matches. If we look at it in more details, at the location of the match in one image, we compute the corresponding 3D scene point using the current pose estimate and the render depth from the NeRF. We then project this 3D point onto the other image. Our multi-view correspondence loss minimizes the distance between the original key point and the projection. While we only show it for one image, the actual loss is computed for both images. So we can see that this loss provides supervision on the current pose estimates and on the NeRF through the render depth. By integrating this loss within the NeRF optimization, it serves two purposes. Through the explicit connection between the training images, it forces both the optimus poses and the scene geometry to converge to a globally consistent and geometrically accurate 3D solution. This loss also enforces the render depth to be close to the real surface. At training viewpoints, we have RGB supervision, and we can apply our multi-view correspondence loss, so the render depth is likely to be of good quality. On the other hand, at unseen novel viewpoints, we have no supervision at all, so the render depth could have some errors and inconsistencies. It could be of much lower quality. With the depth consistency loss, we try to improve that. We therefore use the depth map rendered from the training viewpoint to create pseudo-depth supervision at the unseen viewpoint with simple geometric varping and filtering. Our depth consistency loss then minimizes the error between the two. This loss optimizes over the neural radiance field weights, and as I said, it will ensure that the scene is rendered consistently from any viewing direction. Now let's look at some results. In this paper, we show results on multiple datasets: DTO, which is object-centered, SSF, which depicts forward-facing scenes, and Replica, which shows indoor scenes. We assume that only 3 views are available and consider different noisy poses initialization. For all datasets, our approach obtains state-of-the-art results. I won't go through all datasets in this video, but if you're interested, do check the paper. Let's have a closer look at results on DTO. The initial poses are obtained by synthetically perturbing the ground truth poses with Gaussian noise. For a particular scene, it looks like this. The initial poses are in blue, and the ground truth ones are in pink. So this is what happens during the optimization. We see that our approach SPARF can successfully refine the poses better than NC-NeRF and BARF. This is shown quantitatively here, where over the whole DTO dataset, SPARF obtains very low rotation and translation errors, much lower than competitors BARF and SC-NeRF. Looking at the rendering quality in terms of PSNR, SPARF also outperforms the others by a large margin. And finally, it obtains the best depth errors, meaning that our approach learns an accurate scene geometry as opposed to all of the other works. So this is a qualitative comparison on DTO. Looking at the depth maps, BARF and RegBARF do not learn any meaningful geometry. For SC-NeRF, the object is well reconstructed from some viewing directions, but it is not consistent across all of the viewing points. It also has tons of floaters obstructing the object in the rendering. Our SPARF instead generates accurate and consistent depth renderings across all views, where the object is well defined. Here, we look at SSF, which is a forward-facing dataset. As input, we assume 3 images and start from identity camera poses. Our SPARF has a lot less floaters and inconsistencies than other approaches. This is another example. We see that our SPARF leads to much sharper renderings than alternative works. In essence, our approach is applicable to any scenes, even non-object-centered scenes like here. As visualized in the depth map, our SPARF accurately recovers the details of the scenes. In this example as well, SPARF has much less floaters and better defined scene boundaries than other works. Thank you very much for your attention. If you're interested, check out our code and website.